and make sure that you can actually get the results that you're looking for. That's all I have for you. We still have a couple minutes if any other voting and or student teams or faculty members have any questions. If not, we can get Team 6 queued up and ready to go. And thank you, Team 5, for your presentation. Well, that was fast.
Hey guys, just doing a mic check for Team 6 here. This is Richard. Can everybody hear me?
Loud and clear.
Thanks, Phil.
Hi everyone, this is Tom Flipson from the University of Washington. I'd also like to do a mic check. Can everyone hear me?
Yep.
All right, people can hear Iowa State. Can you see our presentation?
You are a little quieter than the other two, but we can see your presentation just fine.
Is this better? We're going.
Yeah, that's great. Thank you.
Okay. Good morning, everyone. We are Team 6, Marty, and this is our critical design review. So we'll start with going over our mission statement, examining the mission stakeholders and the description of the mission, as well as some of the parameters that we've designed. So our UAV, Marty McFly, will be flying into extreme storms to collect weather data in order to improve tornado prediction. We'll be doing this using dropsondes that the National Center for Atmospheric Research has very graciously donated to our cause. Some of the stakeholders for our mission are Dr. Robin Tanamachi from Purdue. She's a professor in the Department of Earth Sciences, and she researches severe storms and tornadoes. So she's been very instrumental in helping us determine the types of conditions that we'll be flying in. We've also been working with Dr. Holgar Vomel and Dr. Terry Hawk from NCAR. They're scientists who operate and design the dropsondes to collect the data and then analyze the results it gets. So for our mission description, you see on our left here our flight path diagram. So as you can see, we'll be beginning at the ground station, flying about 1.5 miles to the first dropsonde location, and then we'll be flying along that rear flank downdraft part of the storm to where we'll drop our last dropsonde and then returning to base. Our altitude diagram shows that we'll be ascending to about 2,500 feet as we approach the storm. Once we enter that storm front, we'll be dropping the first 2 dropsondes, crossing the air mass to collect data with the last dropsonde. Once we exit the storm front, we'll be dropping that final dropsonde, descending to 400 feet, and then returning to base. Some of the parameters that we've come up with and requirements are that our UAV shall fly about an 8-mile range. It'll cruise at 67 miles an hour with dash speeds of 88 miles an hour. It'll reach 2,500 feet above ground level for max altitude, be able to carry and deploy those 3 dropsondes that you see on the bottom, and then it'll be able to tolerate any gusts, hail, and water it might encounter in the storm. And then it will finally be hand launchable. Some of our design overview features that you'll see here are we have removable wings for easy transport, since this will be traveling with storm chasers. We have a cantilevered tail boom for structural support, and then our components tray, which holds all of our interior components, will be fixed to that boom. Our dropsonde deployment feature will sit on the bottom of the fuselage and be able to deploy the dropsondes that NCAR has gifted us. And you see those down on the bottom right. These are operational. They will be able to transmit data to us. This is our full assembly. All of the units here are in inches, and you see that we have about a 3.5-foot wingspan and about a 4.5 from nose to tail. Teamwork breakdown is pretty similar to PDR, although a couple things have changed. Pengwei is still our coach here at Iowa State. Brenton and Steven are our program managers and chief engineers. Anwar is also assisting. And then our team has expanded to include 6 sub-teams now. We've added a payload team, and the students have been redistributed according to that. So now I'll transfer it over to Tom and Marcello at University of Washington to discuss propulsion.
Good morning, everyone. My name is Tom Flipson, and I'm a student at the University of Washington. And today I'm going to discuss with you our propulsion design requirements, our design selections and performance for propulsion, and the subsystem validation and testing. The propulsion design requirements for our system, we must provide enough thrust to overcome the drag that the aircraft will produce or will be subjected to at 67 miles an hour of cruise, with a surplus thrust that's available to overcome drag at 88 miles an hour for a short. We also, our battery system must also provide enough energy to allow the aircraft to fly a mission range of 8 miles. And the estimates of this requirement will be validated by measuring the power consumption at various dynamic pressures. On the right, we have written some validation of those requirements, that our propulsion system must provide particular amounts of thrust at particular dynamic pressures that correspond to 66 miles an hour and 88 miles an hour, as well as provide 8 pounds of static thrust. And also the power requirements as well that we will be also checking for as well. The components have largely not changed since the PDR. One exception to that is our selection of our batteries. We have upsized our battery capacity to the 3,000 milliamp hour 4-cell Turnigy Nanotech batteries. We'll have 2 of those running in series to give our voltage will be running at 29.6 volts. And the reason we upsized those batteries was due to an update in our estimate of the coefficient of drag.
Hi, I'm Marcello from UW, and I'm going to be going over the aerodynamics and control slides with you. For aerodynamics, we're going to cover design requirements, our selections, what we expect that to perform at, and how we'll validate. So for our requirements, we want our UAS to be able to tolerate a 67 mile per hour gust, which we pulled this number from a research paper on mesocyclone UAS research. We want to be able to fly up to 2,500 feet above ground level so that we have adequate drop time for our sensors. We want to be able to survive for reuse on landing so that we can hot swap batteries and reload the sensors. And we have a 8-mile round trip distance because we've determined 4 miles is a safe distance to stay away from the weather pattern. We need efficient cruise and stability for these types of conditions. Obviously, we need to be able to resist gusts and define and to fulfill the mission as defined earlier by our stakeholders. So the next few slides are our wing selections. For the main wing, we went with an MRC-16. The high thickness is going to allow for sufficient lift and to embed our servos, while the low camber is going to provide an acceptable pressure gradient to keep flow attached. These 2 airfoils shown are vertical and horizontal stabilizers, and what's basically important to take out of this is that since we have a large moment from our main wing, we needed to size the airfoils in the rear of the aircraft to counteract that. So for performance, we're going to be mounting at a 1.2 degree incidence angle, and we're expecting a wing loading of 140 newtons per meter squared during cruise with a max load of 12 Gs beyond that. Okay, validation. So you can see a wing that we have mocked up from Purdue. It's a foam core with a fiberglass flay-up. We're putting a Kevlar leading edge for damage resistance for hail. And we're going to test that in a wind tunnel for hand launch speed and stall speed. And then for cruise speed, we're going to be doing software validation. So this graph is showing how our X-Flyer 5 data compared against wind tunnel testing. And what we see is that at about an angle of attack at 10 degrees, the data basically matches up with each other, with X-Flyer coming in a little underrepresentative. At 10 degrees, in the blue line, you can see we start to see separation with full stall at 14. And the reason that the two lines diverge from each other is because the software wasn't able to predict our stall. Okay, here's basically a second validation from star CCM. Again, if you look at the x-axis at about 10 degrees, you see a tapering off of lift while drag continues to increase, and we're also able to see an optimal launch angle of 3 to 5 degrees based on the lift over drag curve. So since we were confident and satisfied with the way that our wind tunnel data matched up with our software validation, we're going to use star CCM to validate our cruise configuration. And this is going to allow us to, one, save time without having to go to the wind tunnel, and two, we'll be able to change around our angle of incidence much easier to really hone in on the appropriate value. Okay, the next few slides are our control selections, and again, we'll go over design requirements, selections, performance, and our validation plan. So for an aircraft that's going to be flying near tornadoes, we of course need high stability and control authority. It needs to be durable. We need to be able to operate in varying speeds, which is the cruise and dash speeds that we talked about earlier, and we need extra lift for takeoff. So to achieve that, for high control authority, we're going to be using strip ailerons, which run the length of the wing. We're going to have a flaperon configuration so that we can improve our stall speed. The elevator is going to be a stabilator to counteract that large moment that we had from our main wing. And we're going with a conventional rudder with a leading edge taper. So because we are expecting high loads on our wing surfaces, we're going with high torque servos. For the flaperon, we're using 2 Spectrum A5060s, and for the stabilator, we're going with the MKS HV60. And the graph on the right just shows what our expected torque is going to be per applied voltage. And I'm going to pass it over to Richard to talk about structures.
Yeah, thanks, Marcel. As I said, my name is Richard. I'm going to cover the structure stuff for you today, and then a little bit on how everything's going to integrate. So for structures, we're going to talk about the requirements again, the selections we made, and then some validation analysis of that. So the requirements were, we need to tolerate 67 mile/hour gusts. That's about 30 meters per second. We need to withstand hail impacts. Obviously, if we're going into these big storms, that's a concern. We need to be able to withstand belly landing impacts. That's how we plan to get to the ground. Be water resistant, obviously to rain. To carry and deploy 3 drop-sons, that's the payload we talked about. And then to provide access to the internal electronics, if we're hot swapping batteries, we have to have reasonably easy access to get in there. Okay, just a look at the interior component layout. On the bottom, you can see the drop-sons. That's what we will be dropping in the storm. On top of that, the electronics tray. This is where everything like our batteries, our Pixhawk, and our ESC will be located. Of interesting note, the 2 fuselage brackets, which hang the electronics tray underneath, it's sort of hard to see in this image, but those are clamps. So before full bonding, we will be able to have some degree of freedom to move that, which will help give us a little bit of fudge factor with our CG. The fairing is attached to those brackets as well. Of note with the fairing, it's a clamshell design, so we have these 2 arms that go together. It's fully symmetric with regard to front and back. That way we only need to make 1 mold, which will help with manufacturing time, make things a little easier. Because of that, however, with the motor being different and the tail boom here, we are also going to craft a our fuselage plug just to get rid of a large drag surface back there and make it a little more streamlined. A little breakdown of the wing assembly. We have the mounting bracket, which once again is kind of a clamp design, so that will be translatable and give us some degree of freedom when getting an estimating RTG. That will attach the wing via 2 spars. The wing itself is a foam core with a carbon fiber layup on top to give it the structural rigidity it needs. Tail assembly in similar fashion. We have the stabilator, has a spar going through. on either side, and then the vertical stabilizer. These are all once again going to be foam core construction, and then with a fiberglass or carbon fiber layout on top. Some structural analysis. We conducted some FEM just to make sure that some of our selections would be able to handle the loads. So we constrained it at the interface between the bracket and the tail boom, so right there in the center. The loads we applied, we picked on a load factor of 1.5 times our expected gust loads, so 1.5 times 8 gave us about 12 Gs. We had a wing loading of 140 newtons per meter squared, and then that's just because of the maximum gust of those 30 meters per second. That's a down gust. What we found was a spar factor of safety of about 2.56 and a bracket factor of safety of about 1.71. So at this point, we're reasonably confident that our structure will be able to take some of the loads applied. A little bit of systems integration, so just how all the components are going to work with each other, and then a talk on some power systems or other electronic systems components and the power budget for those. So this was the integration plan. This started as actually a block diagram, so if you can imagine where the picture of our aircraft is. That is our tail boom. Everything seems to stem from there. It's a commercial off-the-shelf component, reasonably controlled. But then how everything reacts to that, you can see, for example, the wing mount comes off that boom, and then via bolts that is attached. The wing assembly is attached again via bolts to the wing mount, and then the spars, the servos, and the flaperons are all attached from the wing assembly there. Similar with the components tray and the motor assembly, basically seeing how everything interacts physically and how it can be broken down into these subsystems helped us distribute it among the different universities and helped us understand who would be interfacing with in terms of component design and so forth. So electronic systems components, power systems components. This is a rough wiring layout. Subject to change slightly. Of important note here is we are running separate power and signal lines. We can't power the servos directly from the Pixhawk because with the high torque, we're going to need a little more voltage coming through there. So we're probably going to have to run a separate rail out to each of those, potentially as well for the actuators. And then you can see everything else should talk through either a signal line or a power line. Power budget, so all the non-propulsion components, we have the Pixhawks, the servos, the actuators, taking best estimates of the data available. A total watt-hour needed to run those components is right around 7. The expected energy we need for the propulsion components and just for flight is around 60 watt-hours. That gives us a total of energy of about 67 watt-hours. The total stored energy in the battery system we selected is about 88 watt-hours, and that gives us about a 12.5% surplus. Just a fudge factor there if calculations were off, or if we end up needing to fly a little longer. All right, I'm now going to pass it over to Becca to talk about further validation.
Thanks, Richard. So we'll move through the glider that we built this semester, our plans for testing the propulsion system, flight testing plans, and payload testing. So as you can see here, this is the glider that we built. It's the same wing that we tested earlier this year in the wind tunnel at Purdue, and it's been mounted to a representative fuselage, tail boom, and then a tail to illustrate the full dimensions of our glider. Our propulsion system testing will be conducted at the University of Washington in their 3x3 wind tunnel, and the purpose here is to validate that the power plant is going to produce the thrust and power that we need, to ensure that the battery capacity is adequate, and then also to validate the estimates of thrust, torque, and advance ratio that we've been using for our calculations so far. For flight tests, we have 4 weeks of flight testing planned. The first week we'll be investigating glide, stall, and cruise conditions for the aircraft. Week 2 we'll move into investigating dash velocity, climb rate, and then range and endurance for the aircraft. Week 3 we'll be looking at the payload deployment. We'll be looking at both high speed and slow speed deployment based on the various flight conditions we might encounter. And then week 4, our contingency testing. We'll be looking at loss of signal as well as full control deployments. For our payload testing, we'll be doing structural integrity testing on that drop-down mount that you see up in the top right. So we'll make sure that that can withstand any kind of loading that it might encounter during flight, And then we'll also be looking at battery life and radio range for the drop-ons that you see below. These have internal batteries, so we'll just be making sure that those have the life to last for the whole flight. For payload communication, each drop-on is connected to one of these handheld radios that will be receiving data, and we'll be working with NCAR to help us put those in communication, and then also with software providing for that data analysis. And I'm going to give it over to Brenton to talk about manufacturing.
Thanks, Becca. So to go into our manufacturing phase and our production readiness review, we're going to go over an overview of our plan, a sample plan, jigs and tooling we might use, our timeline, and finally our manufacturing map. For manufacturing map, we have a couple branches. First, we have the motor assembly being produced and tested at the University of Washington. The aluminum wing mount and bracket fabrication will be done at 3VCC, and Purdue will be working on the fairing manufacturing, wing manufacturing, and component assembly, while Iowa State works on the drop-on assembly and tail manufacturing and assembly. As you can see, we've accounted for the delays due to shipping these parts to the different locations. So our manufacturing sample plan, this is just an example of our bracket used to hook the tray to the tail boom. You can see we've outlined where it's going to be sent, the cost, possible materials, tools required, 3-view drawings that can be given to the manufacturer for fabrication, as well as a procedure for how to use it and the intended use. For jigs and tooling, throughout this process we'll be using quite a few different fabrication tools. At Iowa State, when we produce wings or our tail assembly, we do it using a Mastercam and a CNC. In the image it shows creating a negative mold for the underside of the wing section so that we can correctly CNC the top part. We will also be using 3D printing. So manufacturing timeline, I'd like to draw attention to the legend. So the building time takes place in the black areas, the shipping time takes place in the gray area, and the testing in the yellow. For example, the drop-on assembly will be testing some of our components and then building our final assembly before testing it again and make sure everything works well before shipping it off to the main assembly. Throughout this up, we have our project management. We'll be outlining our updated budget as well as the Phase D schedule. So for budget, as you can see from the pie chart, we still have quite a bit of a remainder left over. Our total project cost is about $3,878. We have accounted for the shipping expenses in there. Our payload is very, very small amount of our overall budget due to the generosity of NCAR providing the drop-ons. We won't actually have to purchase those. So Phase D schedule, this is just kind of to go hand in hand with the manufacturing plan. As you can see, all of the fabrication and testing are integrated here, as well as some other things that don't rely, that don't fit directly into the manufacturing plan. So thank you for listening, and we'll open up for questions.
Looking at your attachment brackets between the tail boom and the wing mount, I'm not sure exactly which slide is that. You scroll back where you're showing the fuselage attachment, wing attachment to the fuselage.
Kind of an image of the one you're referring to?
Yeah, if you go further up, there is a better one. Yeah, you just passed it. Okay, that one. So for the intents and purposes of this model, this is a adequate design, provides you flexibility and adjustments. However, if you would design wing to fuselage joint like this in Boeing, you would receive a lot of constructive criticism. Generally, you're trying to avoid putting your bolts in tension. Your fasteners are way more efficient if they're loaded in shear. So this is something to consider, just a word of advice.
Excellent, thank you for that. Yeah, we'll work on the right thing.
I think it will do just fine for what you need, but what I'm saying is this is just a looking forward. One other thing is you have protruded carbon fiber spars. I would consider putting a very thin wall metal sleeves in the areas where the parting plane is between your fuselage attachment and the wing, and the same at your tail, horizontal tail attachment to the fuselage. As I mentioned before, carbon fiber doesn't like to be point loaded in a transfers to fiber direction. It's pretty sensitive to that auto plane loading, so you may want to have something to protect that immediate area.
Excellent. Thank you for that insight.
That's all.
Are there any other questions?
I'll pitch one your way. I believe early in the presentation, like slide 6, so kind of your initial view. Just kind of that would work as well. Just kind of anything that shows the entire aircraft as you currently have the design. If I would look at that, I would say it would be impossible to get your CG where you want it. That being said, I think there were some points later in the presentation where the location of the wing looks more reasonable, although it's not on your tree view. I just would like to warn you, hefty, like, I don't know, quite urgently about that. We've had groups do that before, and you can't put enough weight in the front to try to get your CG where you want it. Did you have a CG breakdown somewhere? I don't know that you did.
No, we didn't bring that forward from the PDR.
Okay. Especially, you show your internal arrangements. Unless your motor is made of like depleted uranium, I don't think there's any way that you can get the CG. But I would love to be proven wrong on that. Proving that would be an excellent thing for this presentation, or at least reminding us. And then I guess one of my other questions was kind of along what Bronco had said. What is your plan about integrating your spars, or keeping your spars in place either in the wing or in that central box structure?
So I believe, Patrick, I believe you're on here, kind of worked with the wing mount and integrating that. Can you speak to that a little bit?
Patrick, I think you are still building.
Go ahead.
Yeah, so for the wing bracket, so the spars we're thinking of epoxying them into the of the wing, so that way they'll be fixed in there. And then for our wing mount, it'll be slid into the spars will be connected there, and then our foam will be touching the sides of the wing mount. That'll also have a little bit of epoxy to hold it in place, to hold it centered in the center of the wing.
So it's a permanent closure?
It is.
Okay.
The entire wing assembly will be a one permanent piece.
Okay.
So our removal aspect will be from the wing mount and not necessarily the wings off of the mount. It'll be the mount off of the whole assembly.
Oh, okay. And I don't think you do just yet. Do you have what's your plan about mounting your fuselage skin? Right now, it looks like it's just kind of floating.
Okay, so in this image that we're actually looking at, the very top of the bracket that attaches the plate to the boom, there's a small cylinder that rises up and there's a small hole on top. We'll mount it on top in the front and back there, and then on the bottom, the piece that integrates the drop son, that holds the drop sons, there's also heat inserts there, which can also do screws. We'll be attaching it from the top and bottom for each half.
Okay. And then do you have any plans about waterproofing the fuselage at all?
Yeah, so with the clamshell design, that's kind of a challenge. So we were thinking about some small rubber lining around the outside, like when you press them together, that would create the waterproofing aspect. As for the drop sons, that'll obviously create a hole once we release the pylon. But since the 3D printing part covers up the hole as well, so we believe that should block it out. Need be, we've also been looking at the waterproofing spray for isolated places.
That was the last one I had. Anybody else has questions? I have a couple of minutes.
what is your sensor release mechanism for the three shells under the body?
Yeah, so as you can see in this image, we're still working on the detailed design of how we're attaching these, but at the bottom of the image, there's three small linear actuators that would release the pin from these 3D printed pylons that are mounted into a kind of a square mold at the bottom. That way we can avoid any heel towing from any gust that might come onto the drop zones. And then I know Becca spoke with NCAR a little bit more about this, and they said, so our plan was to epoxy these small pylons into the center of the drop zones, and NCAR doesn't see any issue with doing that out in the field. Yeah, there's a little bit clearer image of our drop zone assembly. Anything else?
Just a little comment. You just passed this two slides before your mounting plate for that one. You have mounts at each end, and then you have some equipment mounted in the middle. It's a relatively thin sheet metal part. Make sure you have enough bending capabilities.
Yeah, some FBA will have to be done on this to ensure that the mounting.
All right. Thank you, Team 6.
Thank you.
And last but not least, let's move on to Team 4. My team, who is suspiciously absent from